Oh, big. It's a bit strange. So can you see the full board now? So Vyacheslav, because it suddenly changed in Zoom, so I don't know, but I guess so. So yes, yeah, it's blurry. Yeah, yeah. Then I will put it. Just use the part. Okay, I see. I will write bigger then. Here. Readable. Let's check. Yeah, it's hard to see. But yeah, I will write a bit bigger and I have one better marker. Oh, yeah. Some rescue. Okay. Yeah, so today it's about thank you. It's about probabilistic computation. So all our algorithms we discussed so far are deterministic. Sometimes only so sometimes you can do something faster if you involve probability. So the most famous example is polynomial identity testing. So I will first for 10 minutes give some examples on problems where it helps just for fun. You don't need to remember anything. Except for polynomial identity testing. So the input is polynomial in many variables, and you can write it using brackets, multiplication, and addition. And so you receive two you receive two polynomials. Question is, are they always equal or equivalent? You get one polynomial, is it always equal to 0? And so one can say, if I get a polynomial x plus y times y plus z, so when I have products, I can always expand as a sum of products. And then if everything cancels, they are equal. But you can guess where is the tricky part. Yeah. So if you have a bunch of multiplications like this, you get exponentially many factors, and there is no way to know whether polynomial is identically 0. However, in the exercise, in the seminar, you will see if you assign random values to check whether a polynomial is 0. If it's non-zero, then for random values, it will evaluate to something non-zero. And we know multiplication and addition can be done in polynomial time. And so we just have to check that value is not too big. But at each polynomial, yeah, I can take it. Okay, so so here is a problem, and we know we can solve it in polynomial. So you will see in seminar solvable in polynomial time with probability. However, there is no polynomial time algorithm known that works deterministically, and it's kind of very special problem. So for all problems that are known and people know probabilistic polynomial time, they manage to invent deterministic algorithms. So therefore, they think that probabilistic polynomial time is equal to, probabilistic polynomial time is equal to deterministic polynomial time. So it was a conjecture, and actually many people think it's true. Okay, let's wait a bit when it's silent. That's how. Okay. So yeah, so people think that these two classes are the same, but there is no proof yet.
probability polynomial.
Yeah, so can you answer, so decide language using probabilistic algorithm in polynomial time? The precise definition I will explain soon.
And it is a question that it is equal to deterministic
polynomial time. And so basically the only question, a precise example for which there is probabilistic polytime algorithm, but no deterministic one, is polynomial identity testing.
It can also be not like probabilistic complete stuff.
Yeah, such a class doesn't exist, so that's complete for. I'm not so it's kind of empirical thing. It looks like the hardest problem, but and I don't know how to reduce or how to say that every probabilistic algorithm reduces to such a. Actually, I didn't think about this question. Maybe there is a way to. Okay. Yes. Okay, so there are 7 more examples. For example, randomness often helps to speed up some existing algorithm. Most famous one is primality testing. So for crypto, your computer needs prime numbers. And so it will take random numbers and check whether it's prime. So it runs prime checking a lot of times and on many PCs. So there is Miller-Rabin test. It runs in quadratic time, and it's probabilistic test. There is the deterministic test. So 2006, some famous paper. But deterministic algorithm runs in n to the power 6. So if you have an n-bit prime, it is way too slow to be useful. Another example is median finding. So you can, there is kind of probabilistic algorithm that works in linear time. If you have n numbers, you need to find the median. And it like randomly removes big parts from the list in equal chunks, and then it does it many times, and with certain probability you get the correct answer. And deterministic algorithm is n log n time. So I just took the example from YouTube movie. So there is a link on the wiki. Yeah,
I definitely know a linear, non-probabilistic linear solution for finding median. And element can be solved in linear time without probabilistic.
So how do you do it in linear time?
There is a tricky algorithm. It's called medium of 5. It's hard to explain. It's very complicated algorithm, but it runs in linear time. And there is it was in lecture in chat.
Oh
yeah, it's good.
Oh, sorry, I didn't know about. Okay, let's check this details. Yeah.
Okay.
So we also need to check which model and so on. Okay, so verifying that 2 matrices are the same. So you get a product of 2 matrices, whether so you get 3 matrices, this product of 2 equal to the third one. So according to so there is very good teacher, now I forgot his name, but the link is on the wiki, and so he explained that best algorithm, basically deterministic algorithm, is basically to multiply both matrices and see whether you get the third one. And so runtime, do you know what's the runtime for multiplication of 2 n by n matrices? So trivial algorithm is n to the power 3. And so every column goes here. But there is very weird algorithm that goes, well, this Weierstrass algorithm, 2 to the power 7 something. So, and then there is crazy improved algorithm that's not used in practice, 2 to the power 3. So that's the best. But with probabilistic algorithm, you can multiply by random vector, do it in n squared time. So another one. Then computation of minimum spanning tree apparently goes in linear time. I don't know the algorithm, but deterministic algorithm is not linear, but n times inverse Ackermann function. So theoretically, it is unbounded. Ackermann function is really fast-growing function. It's like faster than tower of exponentials, or a tower of x, and so on. So theoretically, so in practice, inverse Ackermann function is just a constant, but in theory, it's kind of slow. Then there are three more examples. Okay, now it's very famous problem is three-sat problem that is NP complete. And so deterministic, this is a bit funny. So a deterministic algorithm can do better than brute force. So brute force is 2 to the, so you can first apply a variable reduction strategy. So the number of variables is proportional to the length, well, it is bounded by number of clauses. And so there is, okay, but this is not relevant. So if there are n variables, best algorithm is n to the power 2 to the power n to just brute force check, but you can do 1.34 to the power n. So there is clever way to speed it up, but the probabilistic algorithm you can do slightly better, 1.31 instead of 1.34. So this is kind of funny. Okay, so there is bipartite perfect matching problem. So you get two sets and a bipartite graph on them, and you have to find perfect matching, and it can be parallelized with, so there exists probabilistic circuit. You can solve by probabilistic circuit with log squared depth and polynomial size, but for determinist, so probabilistic circuit is circuit with extra input in which you put random bits. And by the way, the homework question is like this. So if a homework question of this lecture last year was not so good, I don't know why. So you have to just listen to theory lecture that PVP is and P/poly, and it uses error reduction, and just do the same thing, and everyone should have a good grade. So it is, some people had half of a grade on this last question. And one person had full grade, but it was not so good. But I kept the question from last year because I think maybe there was some other deadline or something. So just pay attention to last result. Okay, so what I'm saying is that perfect bipartite matching, there is no deterministic algorithm that solves it with NC2 circuits. And then people from theoretical computer science lab, they were thinking on it, and there was some guest that came who had made some improvements on algorithm. But okay, still no NC2 deterministic algorithm, only polynomial, only probabilistic circuit. However, there is quasi-polynomial circuit of depth log squared n. So there is almost NC2 deterministic circuit. Okay, so then that's basically the examples. So for polynomial identity testing, it works really, it's really important randomness. And for the other examples, we just need it for speeding up. Next lecture will be about approximation algorithms. So most things will be probabilistic, most others. We will have many more examples. Okay, so now let's start with the theory. So let us define the class RP. So this is so we will have Turing machine that's similar as non-deterministic one. It has two transition tables, and now the idea is that every step a random transition table is chosen. And in the class RP, we have one-sided randomness. If word is in the language, machine must accept with high probability. If it's not in the language, machine should always reject. So it's very close to a definition of NP. So in the computation tree, so it's an RP if at least half of the leaves in the computation tree accept. And if input is not in the language, all leaves should reject. So that's definition. So let me write it.
R is for random.
Yeah, random polynomial time, and it's one-sided randomness. So yeah. So we say that language L is in RP if there exists, but I will call it randomized polytime randomized Turing machine, and
With two tapes, yeah.
any number of tapes. So just standard Turing.
Any number of tapes, and we choose the tape.
No, the two transition tables. Yeah. So the transition table given state and input under the read.
Two transition.
Yeah, like NP machine, with machine for non-deterministic polynomial time. So runs in polytime. So here n is the input length. And then there are two conditions. If the word is in the language, then the probability that MW accepts is bigger than 1/2. And if W is not in the language, then probability MW accepts is equal to 0. So I say again, we want that in computation 3, there are many leaves that accept. For definition of NP, there is just one leaf. Now we need many leaves. Okay, so this is the definition with randomized Turing machine. Now there is a second definition. Hello. The second definition, where we consider deterministic Turing machines that have a second argument. So definition 2. Definition 2. So let us say L in RP tilde if there exists verifier. So polytime verifier, we use the same thing as in the definition of. So you remember polynomial time verifier, it's deterministic Turing machine that receives two inputs, and it should run in time polynomial in the length of the first input. Such that, and then the same thing, if W is L, then probability for a random second input, I will call it C in 0, 1, P of length of W. Polynomial time, I need to give a name, WC accepts is bigger than 1. And so there must exist many certificates if W is in the language, and otherwise, if W is not in the language, it's a bit boring. Then probability. And so then for every certificate should be rejected. For every C in 0, 1, polytime of W and MWC rejects. Okay, and so both definitions are the same, and I guess you will already understand why this is true. It's too easy, or so you should remember from the lecture of NP. And so imagine that we have such a probabilistic polynomial time Turing machine. How do we construct a verifier, polytime verifier? So how will it operate?
On each step, there is a choice like 0 or 1. So this sequence of zeros and ones is the certificate.
Yeah.
And vice versa.
Yeah, so here we have two transition tables, but only one argument. And so verifier will simulate this machine, and it will, to know which transition table it will use for computing the next step, it will use the certificate. And so if this machine accepts with probability 1/2, then we can make, then for randomly selected certificate, machine will accept with probability 1/2. And the same for the rejecting statement. And opposite, and so imagine that we have polynomial time verifier. How do we make, how do we simulate it on non-deterministic machine? We guess the certificate. Okay, this was too easy. I see you're getting tired because it's too slow. That's good news. So let's go to the second definition. There was one more philosophy I didn't tell you. So there are two philosophical objections or practical objections that one might have against using randomized algorithm. First one says, oh, here we have probability of making a mistake of 1/2. I don't want such probability. Imagine that the task is really important. Then you want to know the answer for sure. Second thing is, where does the randomness come from? And so replies to this is, first, we can have error amplification. And secondly, there are pseudo-random generators. So depending on some conjectures, so they come from one wave function, you can create pseudo-random generator using special technique. You should have course on one wave function, some of you have it. And also in software engineering, some people are interested in security. So they learn about all this. So this pseudo-random generator, so getting the randomness in practice is very cheap. And now let's speak about the probability reduction. So imagine that you want to know the answer with probability 2 to the power minus k. So how can you get it? And the answer is, let's run the same algorithm k times on independent randomness. And so if W is in the language and we run it k times, then what is probability that we don't get, so algorithm k times, and if one of the runs says yes, it's if one of the runs accept, then we accept the input. So what is probability that we don't see a one at least one time if we run it k equal 100 or something? It is because the randomness is independent. We have 100 independent runs. Probability to fail 100 times, to have bad luck 100 times, is like 100 coin flips and have all 100 times 0, 2 to the power minus 100. So hardware failure or even meteorite coming by light speed from outside the galaxy and killing us is much bigger than just, yeah. So if your answer is important, well, run it 100 times for your RP problem. So this is really cool. And so here is some answer. Okay, so there is a class ZPP. So it's, yeah.
If we run 3 times, the
Yeah.
machine should not be equal. All machine.
Yeah, the answers might be different. That's
So
what
all machines should be unique.
No, the randomness in the machine.
Transition table. All the transition.
Yeah. So the transition table, they get randomness.
They should be unique for all k.
So 100 times we generate different randomness to run the machine. And so if the randomness is independent, then also answers are independent. And then we go down. Okay. Yes.
Can you explain why the mistake appears here?
Yeah. Okay. So
An example. Why?
Yeah, so what happens here? So we have if we fix W, we have a computation tree, like in the problem NP. So the machine has two transition tables, and it randomly chooses one of the tables to make the next computation step. So if it makes whatever 2000 computation steps, you have all the possible choices can be represented in a tree. So there is first computation step, second one. So here are the transition tables, and so on. So after when the computation finishes, we have a certain amount of leaves. We say that the machine runs in polynomial time if computation always terminates after at most polynomially many steps. So now let us say that it runs always in exactly poly n time. Then the tree is binary tree of fixed depth. This probability is now the fraction of leaves that accept.
So the half of leaves
Yeah.
are acceptable.
Yeah, they must accept W. If W is in the language. So that's the requirement. And so, for example, you can take primality checking, and there is some simple test to check. So you want to know whether P is a prime number, and then you compute. Oh, actually, I forgot what was. Somebody remembers. So it's something like B to the power P minus one modulo P.
It's Fermat test.
Yeah, Fermat test. It's the first part. Yeah. Let's just keep Fermat test. So it works for almost all numbers except Carmichael numbers. Okay, and it's proven. So B is a random number of certain size, and it's proven.
Which is
Yeah, so random number between 2 and B or something, and it's proven
which is
that.
comprised with P, should be comprised with P. P should be comprised with P. It should be a random number.
Yeah, that's called prime. Okay, so random number in certain set, and then number theory, for those who follow it, they know that half of the B's are of the good type. So if this is equal to so if P is prime, this is equal to 1. But if P is not prime and not a special, very small, strange number, then half of the B's will have this different from 1. And this is a proof that number is not prime. And so composite is problem in RP.
Yeah, it's always one for any.
Yeah. If P is prime, it's always 1.
No, it's always one even for non-prime things. Because it's Taylor's theorem.
Yeah, but Euler theorem is for P prime. So then you have field of size P minus 1, and I forgot the details. And yeah, it's some time ago since I studied it. Okay, but the rule, and so this works for half of the P's that you take between 2 and P.
I believe if you take P minus 1 divided by 2, then you get Euler's test, which is like for if B is
Okay, I think this is what I remember. Maybe it's something else. There doesn't matter. There is a set of B's, and half of them give you a proof that the number is not prime. So composite is problem in NP. But to guess the factors is kind of different. You have to guess them exactly right. It's really small probability. But with this number theory magic, you can guess B with high probability. You can guess some B such that it's different from 1. So that's the example. And so our certificate C will be number B.
The time of randomized Turing machine is depth of the
Yeah,
tree.
depth of the tree. So
Okay.
number of steps, maximal depth of the tree. Okay, so when I say leaves on the computation tree, if the leaves have different depth, I mean, if like one branch stops after one computation set, then of course the sleeve has much more weight than the probability. So, okay, but these are details. So let us continue. Okay. Yes,
What is verifier? Verifier and.
yeah. So this from the definition of class NP. So it's Turing machine that has two arguments, input of the length from the language and a certificate. And it must run in time length of the input. So this is precisely from definition of NP. But now we will generate certificate randomly. Okay. Well, it's enough if you understand one of the definitions for the lecture. Okay, so now next problem is class O. There are some simple relations. So we have that P is a subset of RP. Because of course, machine can, we can take 2 times the same transition table, or machine can ignore certificate, and this already explained. Okay, time for next definition. So it class ZPP, it means zero error probabilistic polynomial time, ZPP. So what is it? It's machine that may compute for longer than polynomial time, but when it stops, it must output the correct answer. The requirement is that expected runtime is bounded by polynomial. So with small probability, it can compute very long, but when it computes answer, when it gives answer, it must be correct. So L, new definition, L is CPP if there exists randomized Turing machine M with expected runtime at most some polynomial of n and probability W equals L of W. Here I mean the function that's 1 if it's in the language, 0 otherwise, characteristic function is equal to 1. So note that if expected runtime is bounded by a polynomial, then machine will halt with probability 1. It cannot happen that with probability 0.1, machine never halts. Or let me, okay, this is a stupid way to write it. Let me just say, whenever halts, we have MW equal to L of W. Just the definition. Okay, and so now let's check the relations that are written here. So for people following online, oh, we lost them. No, one is no, sorry, there no, there is one left. So P is a subset of ZPP, and we have this is an RP. So the question is, why is ZPP and RP? So what should we let's check what is obstacle. So why can we not use the same machine here?
Because it can run
Yeah,
longer than.
yeah. So how will we solve the problem?
We can just bound it, like if it runs longer than the nominal time, then we just
Stop it. Yeah, but we
and then
this machine always need to answer something.
yeah, and
except
then and then we use something like Markov's theorem to treat it like constant.
yeah, first the answer will be, so we will use this machine and this definition, but we change it. If it runs too long, we stop it and we answer reject. And so when will we stop it? So if expected time is P of n, so we apply this definition, it's visible, yes. So this is P of n is polynomial. If it runs for longer than 2 times this polynomial, 2 times its expected value, then we stop it and we say reject. Okay, and now we have to understand that probability, if W is in the input is in the language, then it accepts with probability 1/2. Well, there are two cases. Either machine already halted, and then by definition, since it all never lies, it says accept. So we need to bound the probability that the machine did not halt. So probability of not halting is probability that its runtime is twice expected value of runtime. And so probability of M forced to stop. So probability that M runs longer than 2. Probability that time M of W longer than 2p of N is smaller than, so let us say, let's do more general. So longer than t is smaller than expected value of time of MW divided by t. Sorry, yeah, like this. So probability that it runs for time longer than t is expected value of, this is just Markov inequality because runtime is non-negative random variable. And so when we substitute t equal to 2 times expected value, we have at most 1/2, and this is what we need here. And so we need to understand that we break off the machine with probability at most 1/2. And then if this doesn't happen, we are for sure give the correct answer. Okay, so now we have proven that ZPP is subset of RP. Yes.
Why, first you wrote like, expected time less or equal 40 and.
Yeah.
When, like, we.
Yeah, this for
expect
every
much longer
input,
than-
yeah, for every input, expected time at most poly n. With expected runtime of M of W, so for every W. So bounded by poly length of W. This is better.
Okay, okay.
Yeah. Okay, thank you. I was, yeah. Should have stressed that this.
Sorry, and
Yeah.
can you repeat why it is less than one?
One half.
divided by two?
Yeah, so we said t equal 2 times expected value of time of W.
Expected time is,
Yeah.
expected runtime.
Yeah, or the more formally, okay, this is not correct. We said it 2 times the upper bound on expected time. Because we have a fixed algorithm, so we need to hard code the upper bound. And we cannot estimate this. Okay. Yes. So another question. This is in P space. So why is this inequality? This inclusion, I mean. Yeah, this is part of the answer. So what will be the algorithm?
Then we run the randomized machine as many times until the probability is close to 0, exponentially close to 0, and there is polynomially many.
Yeah, but this is deterministic class. You don't have randomness.
Yes, but if the probability is less than 1 divided by polynomial of n, where polynomial of n is
Yeah. Yeah.
some.
NP is in NP in space.
Yeah. Yeah. That's sorry, yeah. That's even better. Yeah. Sorry, that was stupid question of me. But okay, yeah. We know that NP is in P space. Yeah. And do you remember how we proved NP is in P space?
That's really very fun.
Yeah, so we can brute force, so we have computation tree, we can brute force the tree and check if there exists an accepting leaf. And so you can make direct argument for RP. And you can brute force over the computation tree and count all the leaves. But here we don't need this argument. But for our next class, BPP, we will have both two-sided error. And we don't know if BBP is an NP. Okay, but let me first write the definition. And it's very easy to write it. So we say that L is in BPP. Oh, now I forgot. What is it? BPP, yeah. Bounded error probabilistic polynomial time. It's called. And what changes here is that we want probability to be bounded away from 1/2. At most 1. So let us say that it should reject with probability. Yeah, at least 2/3. Oh, this is good marker. Oh, and there are number of online people increased. In the class we have 8 people. So yes. Okay, so this is definition of BBP. Now we allow two-sided error. Both if W is in the language, we should accept with probability strictly better than 1/2. So before people say they had strict, they bound this by 1, they say at least 1/2 accept, and strictly less than 1/2 reject. That's a class PP. It was the first class for probabilistic computation. But this was unrealistically strong class because it contains NP, the class NP. So it is probably exercise in seminar. I forgot if I added this. So, but if I didn't, you can think of why this class. And so class PP, it has at least 1/2 here, and probability of rejecting is strictly, so probability of accepting strictly less than 1/2. It was the class PP, but it's almost useless class. And so, so then there is NP subset of PP. So that means that this PP machine is so so that means at least half of certificate must be accepted and less than half of certificate must be rejected when the length is fixed of certificate. Okay, sorry, but you don't need to remember PP, so let's go back to BPP and put back 2/3. Okay. And now let us ask the same question. Okay, we can again have a definition with certificates. And so now for random certificate, machine should tell the answer, correct answer with probability 2/3.
Right?
Yeah.
If we write just PP, then there is 1/2 there and strictly greater than 1/2.
Yeah.
It's like, it seems like BPP is stronger class. The algorithm is more precise, but the class of language
Is smaller,
small.
yeah,
Oh, yeah.
because the condition is strong. Okay, so we have also a certificate definition. And so here we just, you can guess what will be certificate definition, right? And so there is no expected. Yeah, probabilistic Turing machine here, and then we just say with probability that they are the same is 2/3. Sorry, there is no certificate here. Probability over generating a certificate. So we generate certificate of certain polynomial length. Yeah, and we require that with probability 2/3, the answer for random certificate is the same. And then both definitions are the same again, because we translate certificates in the same way, and things are getting boring for some of you. And so,
So the certificates are now not only for what's in the language, but also for what is not in the language.
well, if word is not in the language, at most 1/3 of certificates should be accepted. Okay, and so now there are certain questions, and so we have again B double inside RP inside BPP, and then inside P space. And now for this inclusion, yeah, for this inclusion, we cannot use your clever trick that BPP is an NP. So it's not known whether BPP is a subset of NP. Not known. So it is possible that BPP is equal to next. Is possible. And so the video is by Guru Swami. This is crazy clever guy who recorded it 3 years ago. So but if this was the refute, so everything we know that does not prevent. So people think that BBP equal P, but actually we know for sure P is very far from next, but BPP could be equal to next. So there is kind of mystery why there is such an extreme gap for precisely determining where BPP is. It couldn't be more crazy open question. So, okay. Yes, but let's go back.
Most of researchers believe that BBB is P.
Yeah, so the from I will speak in the end of the lecture a bit about it. So that there is some quite weak assumption that implies BBP equal P, which is just exist one way function or yeah.
So if we believe that cryptography is possible, then
Yeah. Because then we have a good randomness generator, and we can simulate our algorithm with this randomness. Okay. Yeah, but now our question: why BBP isn't P space? So I almost told the question already, the answer already.
again, we just simulate every possible.
Yeah. And so we brute. Yeah. So let's take certificate definition, and we can just count the number of certificates for which the machine accepts. And then if it's and we take majority vote. If majority accepts, then we are W is in the language and so on. Okay. So we've done all of this. Now error reduction for class R. Yes.
Okay, so how we reach the 2/3 of probability? Like when we work with two transition table time machine,
Yeah.
and
So each time we flip a coin and take one of
Yes,
the
yes.
two.
yes, and that was 1/2. So
Yeah.
half. And why is 2/3?
Well, I explained there was this bad class PP where we had 1/2, where we didn't require. So we had here both something with 1/2. But of course, if we allow both probabilities to be exactly 1/2, it's trivial. Because every machine that randomly flips the language satisfies a condition that just outputs a random coin flip. It will be right with probability at least 1/2 in both cases. So we need different probabilities for acceptance. So probability of accepting must be, we cannot include 1/2 in both parts. And so it turns out that we need to separate the probability of acceptance by a fixed amount. If we don't, if we allow exponentially small gap, then we get a too powerful class. So that's why we have to stay away from 1/2 here. But it doesn't matter. You can put here it's 1/2 plus 0.1% or something. And then from channel, okay, let's so I will now explain that there is a lot of wiggle room with these probabilities, but you cannot take something exponentially close to 1/2, then it becomes a useless definition. I mean, not completely useless, but nothing you need to worry about. And okay, so now I claim that we can make, so let's have a theorem. So if L is in PPT, then we can make a decider that runs in polynomial time and answers correctly with probability 2 to the minus 2n, or 2 to the minus poly of n for every polynomial you want. So let's have theorem here. L is in PPT, then exists a probabilistic Turing machine, a randomized Turing machine, randomized time Turing machine that runs sorry. Search that. Probability that machine is wrong. That marker is red. So probability, oh, that's a good one. Probability that x equals L of x. Oh, I was using double. So bigger. So for our applications, we need 1 minus 2. 2n will be more than enough for our application. So, but you can put any polynomial inside the exponent. If you want n squared, it's okay. So that's theorem. It's called error reduction. Okay. And so, so we start with a machine that satisfies this probability, that answers correctly with probability 2/3, and we need to make a machine that's correct with exponentially high probability. And so before we just repeated the machine k times. Now we will have a machine that will work whatever 100n times. We will repeat the same machine and take majority vote. So that's the answer. So we run it many times, 100n times, and then we take majority vote. Well, let us call this tilde Turing machine tilde. So tilde runs m or under length of W times and takes majority. And so you can prove it by Chernoff bound that this is correct. But we will give a direct proof. So we don't need to remember about channel bound. Okay. So let us make an expression for probability that M tilde gives wrong answer. So then let us think about a fixed sequence of answers. So correct, wrong, correct, correct, wrong, correct, wrong, and so on. So let us think about, imagine that our machine makes, we have to bound the probability that machine makes more than half of this number. So let us call this K. We have to bound probability that we have at least K over 2 mistakes. So let us consider probability M equal to K over 2 to K mistakes. So probability of having, so let's fix M. Probability of having precisely M mistakes. So it is, so we have K runs and we choose M times to be wrong. So this is binomial distribution. It's so this probability, so probability of being M times wrong, probability is so 1/3 is upper bound on probability being lower bound on no, upper bound on probability of being wrong. So I'm computing probability, I'm bounding. So probability majority is wrong. So this is bounded by 1/3 and 2/3. And K minus M. Okay. So now we have to bound this probability. And so let's think about, so this binomial coefficient we can bound by 2 to the power K. All the coefficients. So sum of all, the sum of all binomial coefficients is equal to 2 to the power K. And that's for this other term, take the worst case term. So the worst case term is when K is the smallest. When K is M is this M is the smallest. So we have K over 2 and K over 2 here. So this is bounded by 2 to the power K, 1/3 times K over 2, 2/3 times K over 2.
And multiplied by K.
Yeah, so what we did is we took the worst case for this part.
And then this.
Yeah, and then we sum here. Okay. So this is our bound, and this is equal to 8 over 9 to the power K over 2. And so 1/3 times 2/3 is 2 over 9 to the power K over 2. So I change it to 4 and put it in. So we have 8 over 9 K over 2. Now K is equal to 100 times N. And so that means that so probability to be wrong is bounded by 2 to the power N. So I chose 100 large enough so that all these coefficients are P. Okay, and so we've proven this theorem. So it's pretty short proof. So you can remember it even if, okay, let's say it again. And it's not for everyone again. So we want to prove probability that majority is wrong. And so we run it here, K times, probability majority is wrong. So we need to bound the probability that we have M mistakes. M going from K, starting at K over 2 to K. So here we have a sum where we bound this probability. because making a mistake is 1/3 probability. So up to here, it's clear. Okay, now we need to bound this sum. So what we do is we will look to the worst case factor in front of binomial coefficient. So this happens for m equal to k/2. Okay, so then we have these two numbers with k/2, what we have here. So this is worst case, this part, and then we put the bracket here after we choose m, the worst case value. And sum of binomial coefficient is 2 to the power k. And here it doesn't matter if we take more than half of the terms, it's still 2 to the power k. Okay, but this is not fully correct because, or I can write m tilde here, and you understand the worst case. Yeah, m tilde k. Okay, so now theorem should be clear. The proof should be clear. And we have one task left for today, and 10:20. Yes.
We have some limit of reduction. Like we can rerun the process until we have all runs showing correct answer. No.
Well, the algorithm is just run at 100 length of input time. And okay, that's the algorithm. So you can run more if you want and reduce error further. This you can do. So if you're not happy with this probability of error, you can run more. So not so clear what's your question.
We can run until mistake is 0 or no.
Then we need to run for infinite time. So mistake error increases exponentially. But mathematically spoken, it will not be 0. Practice, it will be 0 very quickly. So we don't care about error probability 10 to the power minus 100. It's yeah.
If we replace the 2/3 with 1/2 plus epsilon, the theorem still works and everything.
Yeah, theorem still works. When we use here 1/2 plus poly n.
Poly n.
Yeah. Plus 1 over poly n.
yeah.
Sorry, 1 over poly n. So let's say n to the power minus some marker. I will switch to your marker. Yeah, that's the result. Yeah, but now the proof is different. Then you need Chernoff bound. Or well, yeah. So this will screw things. Yeah. So 2/3 is kind of special to allow for this factor.
That's
Yeah,
it's very easy to.
it's standard to take 2/3, but yeah, and then the standard choice helps. But it's enough for this. Okay. And then yeah.
What if we do another thing? Well, we run our machine until like number of failures minus number of number of rejects minus
That's
number
maybe
of
what you
attempts
wanted to
is
ask.
at
Yeah,
least
yeah,
something.
proportional. Yeah, 0.
Something like this, yeah.
Yeah, 0.01.
It's probably still works, but maybe it works like faster than faster.
Yeah. So then I think in the proof you can have maybe a little bit expected runtime might be much better. But here it is like we look to the worst case. So in practice, it might be a good idea.
Yeah, that's
Yeah.
purely theoretical results.
Yeah. Since we care about worst case. Okay. Now we only have, so this is error reduction, and this is our last task. Prove that BPP is in P/poly. So that means if a problem is so polynomial identity testing, we can solve with polynomial size circuits. Do you remember P/poly? So for every n, we need a circuit of size polynomial that answers that correctly on n-bit inputs. So online people increase. So was there a problem with vision or something? So I don't know why people disappear. Okay, so theorem.
It's not found about P/poly if it's in.
So we have BPP is a subset of P/poly. Okay. So we already know that P is subset of P/poly. So whenever we have some computation, we can build a circuit that simulates this computation. And the size of the circuit is proportional to square of the computation. And the constant depend on the machine, but once we fix the machine, it's basically the square. Okay. So what is our plan? So plan is just to use a machine that makes exponentially small error. And then observe that if we give it random input, this machine will provide answers for all n-bit inputs with high probability. So with high probability, the same random string will work for all the inputs. So this is because of error amplification. How many inputs of length n do we have? 2 to the power n. What is error probability? 2 to the power minus 2n. So by union bound, probability that we have at least one mistake is 2 to the power minus 2n times 2 to the power n. Probability that we make a mistake on at least one input by union bound is at most probability of making mistake on fixed input times number of inputs, just union bound. Okay, now we have randomness with high probability. So randomness works for all the inputs. So let's fix one random string. Then let's build circuit, P/poly circuit from certificate definition machine. And let's hard code the randomness inside the circuit. And that's the proof. So, okay. I will write it again. So it is our last task for the lect.
And then we use that probability of error can be like strictly less than 2 to the minus n, because there are and 2 to the power of n inputs.
Yeah. So by union bound. So plan is we just need to fix randomness that works for all the inputs.
No, I mean the probability of error is either 0 or at least 2 to the power of n. Can be something.
No, we fix the random. So what we want to find a single value of the randomness. And so we use certificate definition. So we know random certificate.
Like we use the algorithm, which the theorem we just proved, which is already right.
Yeah.
That we can find in polynomial time. That we can verify.
Yeah, I think you're confused with the definition of P/poly. So we have to construct a certificate, but we don't care about computing the certificate.
Yes.
So we just need one circuit of small size. And the plan to get the circuit is to find one random string that works for all, that gives correct answer on all the inputs. Then we go to result P and P/poly, or random is so, or verifier is deterministic machine. We built circuit that simulates it. And this verifier has two inputs, the circuit and the real input. And we found a circuit that works for all the inputs. So we hard coded in the circuit. So that's the proof.
How to prove that
Yeah, let me just go through the proof because so for some students idea is clear. Let me write the statement. So we start by fix n. And then assume machine, so probability that machine gives the wrong answer. And double, and so. And for every W n 0, 1, n. Oh, yeah, this one, right? Of probability, that's how we use certificate definition. For random certificate. 0, 1, p over length of W, which is n. Different from language is smaller than 2 to the power minus 2n. So now let's consider probability for 0, 1 over all the certificates. That for all W n of length n, we have M W C different equal. Sorry, that I need to write the negation. Probability that exists certificate such that exists input such that this is different. So this is clear. So probability for random certificate that there exists an input on which the certificate is wrong. And so here we look at, we fix W here. In the for all, we take a W and then generate certificate. And this is by power amplification. Randomness reduction, I mean. So this machine gets, but now we want the probability that for fixed certificate, all n-bit strings are answered correctly. Here is the opposite. Probability that for some input, we make a mistake. So this will be by union bound 2 to the power minus 2n. And so it's equal to 2 to the power minus n. And so this is strictly smaller than 1. So by probabilistic method, there exists a certificate. So now this one, say, fix certificate inside P of n. So since a random certificate works with positive probability, we can take one, there exists at least one such certificate, and we fix it. Now remember that P is part in P/poly. And our verifier is a machine that looks at pairs of strings. So we have a certificate that evaluates the verifier. But verifier has two inputs, W and C. So now we fix the C and we hard code it in the second input. So we have a circuit that only after hard coding has only one input, the n-bit string. And by construction, it is always correct. It's not this string. So it means it's always correct. So that's the proof. Okay, so it looks that everyone who's awake seem to agree with the proof. Almost everyone.
Why circuit?
Everyone at least half agrees with the proof. Yeah, sorry.
Why circuit is always correct?
Okay.
Why it does not?
Yeah, because we use special certificate. So we know that random certificate is correct on all the inputs. So we take one of these correct special certificates that make verifier always say the correct answer. Then we transform this verifier M to a circuit. And we hard code this special certificate. So then when we give it any input, it tells the right answer. Okay, so I can
But,
explain
but,
one more
but
time.
this-
You need it for the
Why
homework.
is- But these certificates are not always true. It has probability.
Yeah, but we need one such certificate. As soon as we have one such certificate, we can hard code it in the second argument of the circuit.
Look, we prove that there is such a certificate, that it never makes a mistake. And we prove that such certificate exists because probability of so the probability of such certificate exists is strictly less than 1.
Yeah,
And so then such certificate exists, and then we
it's probabilistic method. So we want to prove that something exists, and then we say, oh, but with probability better than 0, we can generate such object. So it must exist.
Okay.
And so here we so if this probability was equal to 1, then we lose. We cannot go with our proof. Yeah,
I got this.
yeah. Okay. Yes, let me check the time. Oh, we have 3 minutes left. Okay, so there is little story in just a few minutes.
a good question.
Ah.
It's not known about this only if it's the next.
Yeah. Sorry. Yeah, of course. Yeah.
And vice versa, it's not known if the next.
No. So sorry. I think no, it should not be in Fish/Poly. I think you can. Fish/Poly should be outside next. Yeah, I don't know. Yeah, it's actually. I
At the
should
start
know.
to connect that BPP can be same as NX and trying to connect it with this.
Yeah, but this has undecidable problems. Yeah.
Okay.
Yeah, but your question is, can we prove that next is not in
So
P/Poly?
it's not made.
I know, but we cannot, it can be equal to BBP. No, so yeah, so it's not known if next is in P/Poly.
Okay,
Yeah.
it's known that P/Poly not in NX, but it's not known vice versa.
Yeah. Okay. Yeah, so, but don't worry about story. In 2 lectures, I have another reason to tell the story. So let's stop the lecture because it is only 1 minute left.
So when the colloquium will be?
Yeah, good question. So this person asked me already. I
Yes.
think 10th of December, it's on the wiki. So it's 2,
So it will be all in December.
so there will be 2 dates. And I don't know how many students we have, but I will need to force students to do it 2 weeks before. So there is the last week of the lecture. So last year I let students decide, okay, I will stop the stream.